Hello, we are Team 3 and this is our design of a Xylene plant. Xylene Chemical is a global producer of commodity chemicals with locations in University Park, Houston, and Philadelphia. Their research and development team has recently been working on a new zeolite catalyst that converts toluene into benzene and xylene isomers. Blaine will be talking about this chemical reaction shortly. The main part of this chemical reaction is the paraxylene, that is the most desirable product of the reaction. Any byproducts from this plant will be used as fuel or gasoline blending stock. We were tasked with determining the potential value of a xylene plant in their current location in the U.S. Gulf Coast. Our plant will be running for 8,400 hours per year, making approximately 135 million pounds of paraxylene per year. The startup of this operation is to occur during January 2023, and it will run for 15 years.
So the main reason we're looking into building this plant is, as Austin mentioned earlier, Xylene Chemicals has recently developed a new zeolite catalyst that preferentially converts toluene into paraxylene with benzene as the other product in that desired reaction. Besides the desired reaction, there are also a couple of side reactions that need to be considered. And this includes toluene dealkylation, xylene disproportionation, as well as the isomerization of the desired paraxylene into its meta and ortho isomers. Although the products for these side reactions are not desired, they can still be sold for profit as long as they meet the 99.9% purity spec. In addition to these specs, there are also some soft specs placed on the reactor in order to ensure that it's running as smoothly as possible. And these include a limit on the amount of benzene and methane that can be fed to the reactor, as well as keeping the hydrogen to toluene ratio at 2:1. In addition to this, the waste of the toluene, benzene, and paraxylene for the process is to be kept below 3%, and the recovery of the toluene for the process is to be over 85%. As for the results, our model was able to meet all of the hard specs as well as the vast majority of the soft specs. This included the benzene and paraxylene products, both meeting the hard specs of 99.9% purity. The mixed xylenes and TMB products were also above 99.9% purity, which means that they could also be sold for profit. Additionally, the toluene recovery was above 85%, the waste was kept below 3%, and the hydrogen to toluene ratio was within the desired range. The only soft spec that we weren't able to hit was the hydrogen partial pressure, and this was to be kept within 1 psi of 250. Instead, our model uses a hydrogen pressure of 248.72 psi, which is slightly lower to avoid coking in the reactor. Next up is Kaylee to talk about the BFD.
This figure shows our overall block flow diagram of the process. So as you can see, the toluene feed and the hydrogen feed mix together before entering into the fixed bed reactor. The reactor effluent is then sent into a vapor liquid separator, which is used to remove most of the light gases, which include methane and hydrogen. That comes out in the vapor stream, and 15% of that is sent to the vapor fuel system, while the other 85% is recycled back into the reactor. The liquid from the vapor liquid separator is then sent to a stripping unit. This removes any remaining light gases, specifically methane, which comes out of the top, and that is purged. Out of the bottoms of the stripping unit, it is then sent into 3 distillation towers. The first one is used to remove mainly benzene, and this comes out of the distillate at a purity of 99.9 weight percent, meaning that it can be sold as a product. The bottom stream is then sent into another distillation column, which is used to remove toluene through the distillate stream. That toluene can then be recycled back into the reactor, and adding in this recycle stream helps us reach the target 85% recovery. The bottom stream of the toluene is sent into the 3rd distillation column, and that removes all of the C9 aromatics or the trimethylbenzenes, and that comes out at a purity of 99.9 weight percent, so that can also be sold as a product. And the distillate stream contains mostly mixed xylenes, so in order to isolate the paraxylene from the mixed xylenes, we used a Parax adsorption unit. So both the P-xylene and the mixylenes come out of that absorption unit at a purity of 99.9 weight percent, meaning that it can be sold as a product. When sizing all of the distillation columns, they all had a length to diameter ratio of less than 30. The benzene tower and the toluene tower had the largest number of stages at 71, and the benzene tower had the highest reflux ratio at 8. Additionally, the overall mass balance is shown here, and that just was done in order to ensure that no mass was being lost throughout the process. This shows a more detailed description of the reactor. So as previously mentioned, it is a fixed bed reactor where the toluene disproportionation reaction occurs. The inlet conditions are 725 degrees Fahrenheit and 393 psi. This operates adiabatically, and so there is about a 15 degree Fahrenheit temperature increase. There is also a 10 psi pressure drop over the reactor. As previously mentioned, we are using a zeolite catalyst. And additionally, we have a weighted hour space velocity entering into the reactor at around 3 pounds per hour per pound catalyst. This weighted hour space velocity was in the middle of the range from the provided pilot data, and this gives us a reasonably sized catalyst bed at 20 feet. Additionally, in the actual process, we will be using 3 reactors. 2 will be in constant operation, and the third can be used whenever one of the other ones is undergoing maintenance or during catalyst regeneration. This will ensure that our process can be continuously operating. Grant will now be talking about reactor kinetics.
For our reactor kinetics, we utilized the Aspen regression model tool so that we could use pilot plant data provided to us by the R&D department to accurately describe our model in Aspen, our reactor model in Aspen. This graph shows our toluene conversion portion of that model against the pilot plant data. The pilot plant data is in blue while our data is in orange. We have an operating temperature range of 650 to 750 with our goal temperatures at 725 to 750. We did this so that we would have a conservative estimate on our toluene conversion. Now, while this does present a difference in the reactor kinetics, it is something that we consider to be a minimal risk because while this is not an exact model, an increase in the toluene conversion would lead to an increase in products, leading to an increase in revenue. So we see the risk as minimal and not something that needs to be concerned moving forward. In terms of our plant utilities, we have utilized a variety of utility sources from refrigerant all the way up to hot oil. We also utilized process streams. So for the total process, we have heating and cooling duties totaling 508 million BTUs per hour. Of that, 168 million are taken care of by process heat exchangers. In addition to that, we use DI water to create low pressure steam, which accounts for another 102 million BTU an hour. From that, the rest of the utilities are taken care of from the other utilities provided. Now, the utilities that we do pay for have a wide variety of costs, with refrigerant being the most expensive even though it has the lowest cooling duty. This is due to the extreme temperatures that we have to operate at in order to reach the temperatures desired in our process streams. This, in addition to a vapor fuel credit that we are given from the hydrogen purge stream, gives us a total utility cost of $15.6 million annually for our process. Next, Zach's going to talk to you a little more about the capital costs involved in our process.
So the total capital costs amounted to around $111 million. This cost included many different factors, including the IBL, or inner battery limits. Consisting within that limit is cost associated with the reactor, other separation equipment, pumps, compressors, and any other design equipment that the team deemed necessary for the plant operation. Additionally, we considered the OBL, or outer battery limit. Within this estimate included the upgrades to site development, environmental, upgrades to utilities, as well as upgrades to the raw materials and product storage. Additionally, other costs such as the initial catalyst loading, team cost, and startup cost are factored into the total plant cost. On top of those three things, we also considered an escalation rate of 2.8% for 4 years. One of those years being for the engineering design, and the other 3 for the construction of the plant. And then finally, to give the team some leeway in their estimate, we added a 20% contingency factor into the estimate to get the final $111 million capital cost. So the plant has many ongoing costs as well that we have to maintain throughout the life of the plant. This includes majorly the raw material cost. The toluene and hydrogen feeds make up a large portion of this, but in addition to that, we also have to pay for the distilled water used for the low pressure steam generation, as Grant had mentioned, as well as catalyst. We have to replace the catalyst in the reactor throughout the life of the plant, and other miscellaneous chemicals as well. In addition to that, we have the utility cost, as Grant had mentioned, the sales, general, and administrative costs, as well as other fixed costs, such as repairs and maintenance, and licensing fees for the Parex unit. And then labor and property taxes are also included in our operational cost estimate. So the design is profitable. We're selling paraxylene at a rate of $7,800 an hour, and we're selling other chemicals, the benzene, the TMB, and the mixed xylenes for $12,000 an hour. As shown on the chart at the right, we can see the blue cumulative cash flow and the orange cumulative present worth are both positive at the end of the project life. Using a discount rate of 12%, we see a 3.27-year payback period and a present worth of $21 million at the end of the project life. This helps us attain after-tax rate of return of 17.1%. So this is above the 15% that was targeted by upper management. So Austin will tell us more about sensitivity analysis associated with our costs.
So a lot can change between now and 2023. So our group analyzed 4 possible scenarios that could occur during this time. We compared those to our base case, and those changes would be maximum capacity, an increase in natural gas price, an increase in toluene price, and the possibility of the plant being built a year faster. And we analyzed those and how they changed in cash flow, present worth, after-tax rate of return, and the payback period. Now, the best possible thing that could happen to us would be if the plant were to be built a year faster. There would be a slight increase in cash flow, an increase in present worth, a significant increase in after-tax rate of return, and a very similar payback period to the base case. The worst possible thing that could happen to our group would be if the toluene price were to increase. Now, it may not be the lowest cash flow, but it still is a significant drop-off from the base case, and it has a present worth of 0, and the after-tax rate of return is significantly lower than the rest, and it is the longest payback period. Kaylee will now talk about the project definition rating index.
To assess how the project was progressing, a project definition rating index was used, or PDRI. This was first done during Gate 3. Upon assessing the status of Gate 3, a score of 721 was determined. The typical range for this stage in the project is 550 to 800. During Gate 4, a score of 589 was determined, and that typical range is 450 to 600. For Gate 5, which is the current status of the project, a score of 413 was determined, and that typical range is 300 to 450. So all of these scores fit well within the typical ranges. If the project were to continue, it would be assumed that these numbers would get lower and lower as more elements became defined. Several key variables that have still yet to be defined are startup, shutdown, and training. Chandler will now be talking about alternate designs.
So the goal of this design was in order to create a chemical plant that would be the most profitable. So in order to validate the effectiveness of our model, we decided to analyze 2 alternative cases to determine the effects it would have on the overall model along with the revenues. So the first of these alternative cases was the inclusion of a hydrogen purification unit within the design. So this would follow the purge stream coming out of the vapor liquid separator, and this would allow our hydrogen to reach a purity of 93%, which would be pure enough to then be recycled back into the reactor feed. By recycling the hydrogen, this would cut down on our raw material costs because we would be able to reuse hydrogen we've already purchased. So this would save us around $6.7 million a year. Now, so the purification unit itself has an additional capital cost of $6 million. The downside comes with the added utilities. The hydrogen needs to be compressed to a very high pressure, and in order to obtain that compression, the hydrogen stream needs to be significantly cooled, which will require refrigerant. And as Grant said earlier, refrigerant is very expensive, so this would add an additional $11.5 million a year in additional utility cost. So because of this would lead to a net loss of revenue, so this alternative case was deemed a poor choice. So the second of the alternative cases was the inclusion of an isomerization unit at the end of the process. So the mixed xylene stream would be flow into this isomerization in order to produce more paraxylene. The paraxylene is more valuable than the mixed xylene stream, so that by being able to convert the meta and ortho to paraxylene, it would increase the revenues by $7.8 million a year. So this was done by looking through research papers, and in the research there was a similar zeolite catalyst that was able to catalyze the selective isomerization to paraxylene to about 71-72%. So this was what leads to the high conversion of the para. Now, the reactor itself is estimated at around $2 million in capital cost, and the catalyst itself needs to be regenerated due to degradation, and this would account for an additional $91,000 every 3 years. So overall, this seems to be profitable and would increase revenue, so this should be looked further into the future and design of the plant. So in conclusion, we propose that our plant design is both feasible and profitable. The paraxylene capacity is 135 million pounds per year. The net present worth of our design is about $21 million throughout the project life. The after-tax rate of return is 17.1%, and as Zach said earlier, upper management required us to have a ROR of 15%. So since we are over that, it shows that we are profitable and we are meeting what management is expecting. The one caveat is we must be able to operate our plant at 93% capacity in order to have a net present value of 0. Any lower will obviously have a negative net present value, which wouldn't be good. So as long as we can meet this caveat, we conclude that our proposed plant design is a good option and we should move forward. Thank you very much.